Hello everyone, this is Mike Tanuri. Today I'll be going over my final proposal for the Nutcracker project in the Design for Manufacturing and Assembly class. So I'll start by giving a brief description of the current design and the goals of the project. And I will systematically go through all my recommendations that affected the assembly, materials, and manufacturing. And at the end, I'll discuss any questions I have for the customer. So as you all know, this is the Nutcracker. It's the first thing that stands out to me is the volume. Since it's going to ramp up to 21,600 a year from year 3 till the end of its life cycle, I believe this opens up some opportunities in terms of net shape processes that could be used for this product, because those can only be justified with volume given the high initial investment in tooling. So the objective of this proposal would be to achieve 50% cost reduction through cycle time or labor, materials cost, process efficiency, or reduction of parts count. So the first few things that jumped out to me as I looked at the design would be the steel bearings. So most of the material in the project were made out of 304 stainless steel, which is a food grade material, but using steel can cause some rusting issues. And since the bearings are not sealed, food might get stuck in the bearings and cause some bacterial infections. So that was a big concern to me. Also, the parts count can obviously be reduced after reading the DFA method in the product design for manufacturing and assembly book. It's obvious that we can reduce the parts count, and at the manufacturing process, just as an initial overlook, I believe the water jetting process was overused. Now, whether that's justified or not, we'll see depending on how I change it and what my recommendation for alternatives are. So starting with the recommendation that affected the assembly and the materials, using the 3 questions that are presented in the book for the DFA method. Do the parts move with respect to one another? Do the parts require being a different material, and will the part be removed for assembly or disassembly? Based on these questions, I decided that I can combine those 3 bottom parts that I'm pointing to with the 3 arrows. So what that will do is definitely reduce the parts count of the overall product, but it'll allow me to have a faster assembly, given that I don't have to align the top plate and the bottom plate. So, and the second recommendation kind of stems from the first one, given that now the 3 parts are combined, we won't need nuts to fasten the top plate. We can just tap 4 holes in the bottom assembly, and the top cover will lay on top and be fastened with 4 screws. So that'll also reduce parts count and save on purchased materials. Now, like I mentioned, the bearings need to be changed to stainless steel sealed bearings, although those have a higher price point. But given that it's necessary to comply with the standards, that's a design change that'll have to occur. Plus, if you think about it in terms of opportunity cost, when the manufacturer gets audited and they find something like that in the machine, then the cost will be much higher than the material change cost I'm doing now. And the last one is a good opportunity to standardize the shaft sizes. So if I can start from the same 1-inch bar stock for both shafts, I'd be saving on purchase material cost, and I'd be saving on the tool changes when I'm drilling the holes where these shafts will go. So I did some calculations for the pinion shaft, and it turns out that a smaller shaft diameter can in fact withhold the forces and the life cycle required for this machine. Now, starting with the drive shaft, I'll go through each component and kind of give my recommendation for the changes in the manufacturing process. For the drive shaft, there isn't much to change. I think all the processes are required on the lathe and the grinder. The biggest change was starting from the 1-inch bar stock instead of the 2-inch, given that it's a smaller shaft diameter. So that'll be saving $18 overall per product. The crusher, I believe, has a grinding process that's not necessarily required. So given that the crusher will meet the wheel at that 3/4 inch diameter, if that was finished by a lathe, it'll give me a tolerance of plus or minus 2 thousandths, which, given this application of crushing a walnut, I think that's more than enough. So grinding that 0.75 inch diameter is an extra step that in this case is not needed and could be saved. By eliminating that, I'll save 5 minutes on my manufacturing time. Now, the top cover, I have right here my suggestion as the future state and the current state. I think the biggest opportunity was to go to a slightly smaller plate, and the whole assembly will be adjusted accordingly, of course. So if I go to a 10-inch by 10-inch by 1/4 inch plate, I'm able to buy this off the shelf, and it's much cheaper than the receiving material that was previously bought. Given that the whole assembly will be scaled, I also don't think that'll affect the form fit or the function. Mostly it won't affect the function of the nutcracker. So then I'm moving into a shorter machining time. So overall, I'd be saving $73 per product by moving to a different plate dimensions and a shorter machining time. For the wheel, I did the same thing in terms of eliminating the water jetting process. I believe the 90-degree angle requirement is an overkill in this case, given that that's where the cracker will or the nut will sit. If it was at a radius done by a mill, that will be good enough for the application. So I replaced the water jetting with the in-house CNC mill, and that saved me $1,800 and 3 to 5 days of lead time for 36 of them. So overall per product, I'm saving about $203. My last recommendation was to move to a die casting process. Given that I decided to combine the 3 parts at the bottom, that allows me to use a net shape process. So I picked die casting using copper. Copper is a food grade material, and it is cheap. Well, cheaper than some stainless steel that are out there. So I have this equation here that helps me calculate the total cost of the tooling, and it turns out that an initial investment of $53,000 is required for the die. But given that we are ramping up to a significant volume, after 350 parts sold, that die would have paid for itself, and beyond that, it'll be only the material cost of copper, which turns out to be less than the receiving material cost that we currently have for stainless steel. So I only had one question for the customer. I know in the project it mentioned that the device is table mount, and I could not understand how will the device be mounted on the table. In that case, that's the question I'll ask the customer, because that might affect some machining processes and might add some manufacturing time. So that's my only question for the customer. Thank you, everyone.